Thank you. My name is Mariano Palomo. I am malware analyst of Entelgene Elotech system. We've changed the name. Now it's security systems. And I am working in reversing malware analysis. And when you see the beautiful thing bad guys do, you're interested in knowing the dark side, the other side of the coin. Well, my email is here, and you can get in touch with me if you'd like to send a feedback or a beautiful picture will look nice. And we're going to start now with this malware analysis and the reversing lab. We're going to have reversing or malware analysis at the workshop in order to analyze all binary and CTF environments, or what's equivalent in the daily analysis we perform. We have here a graph where we have the way I had organized my daily analysis lab. It is what I do to get connected to CTF systems. And here I have the virtual device, virtual machine. I use the software virtualization malware because there are things that are good and they facilitate things and tasks are easier. I'd like to show you that I've connected this to my host, and I have a series of rules applied for the traffic to be redirected towards a proxy in transparent mode in such a way that with a certificate of the user I can breach the HTTP traffic and see requests clearly. For this to work, I have to tell the device that we should use the DNS of your host, the domain system. I use DNS mask with this configuration, the domain server of the host. I have this mask here, and you can copy this directly, and you can have your own lab if you would like to start fighting malware. And on top of this, I'd like to say that as we work with a virtual machine, then they know this, the bad guys know about it, and there are ways to counteract this because there are traces, there are registries, there are footprints, things that are easy to check with programming tools. And if we don't want to have patches all the time to pass the tests, we can change the configuration of the device, or we can then refrain from doing cumbersome tasks. And as I said before, this could be perfectly done otherwise. And there are things I'd like to say, as we saw in the CPU ID instruction at the ensemble. When we put the register EAXA1, the bit 31 that sends us to the, if it is A, it's sent to the call of instruction, it means the instruction is taking place at a virtual machine. If the configuration file, add this line you see here, if you add this first line, the one on top here, then you can get always a 0 from the instruction. In the configuration file, you can say that your virtual machine will be a cloning of the manufacturing of yours. The virtual machine is a clone of the host and the CPU ID. When you use the other parameters, you'll get a string that is used to compare and to see if it is a virtual machine. So you're checking and you're, as you see here, skipping the tests. And then there are ways, perhaps you will see here in a small print, but there are some MAC addresses that correspond to VirtualBox or malware softwares and virtualization, and the configuration in this card. You change this configuration and you put one that looks like your host. And then when they check the hardware, like the amount of RAM memory you have, or for instance the size of your hard disk, the hard disk capacity, the number of processors. When you create a virtual machine, and if you don't have lots of resources, you put something that is not very ambitious, and you use this for tracing also. There are some programs, some software programs that are free, Alcacer and Patches. They have implemented the normal malware verifications to detect virtual machines, and as those are open softwares, you can go to the repository and you can see the code that's checking things, so you can think how to turn it the other way and to see everything green, everything is good when they execute the software. Once we have implemented the software machine, you have to give some tools to the machine facilitating our analysis tasks. I'd like to split this into different categories, and I have here rapid access from the bar, but each one of you can do it your way, do it your own way. And here I can point out in reversing, I have several decompilers for languages like .NET or another software that decompile Flash, other alter it, and there are debuggers like Immunity. I have the old one that it's good still for us, and the modern X32DBG, the modern one. Of course, I have what you see on screen, the graphic user interface that's also useful. And I have Radare, and there are some hexadecimal compiler. We have the 01 editor that is able to have a string in hexadecimal, and you can copy and paste. And for instance, if you have a binary coded in hexadecimal, you copy directly, and you have the binary as such ready for using it and to execute it. And then a normal one, the HXD, or the one that down there that allows you, when you have a memory part, and you can look for it and you can say clean everything to have MZ header, and also the other part can be cleaned. And debuggers to analyze the binary structures are seen here. As we see, for instance, to detect the version of the compiler that's been used for generating the binary Visual C, C++, or Delphi, or whatever. And also, for instance, there are programs like multi-purpose programs to see different things like PStudio and PVia, and to see resources from the executable, the hacker, and when you have a program that has been executed and we want to dump it and we want to keep it executing, if it is not in the memory version, we want to reconstruct the import table, a software like Exila or ImperReg are useful. Then, many times, as we use the vector for entering malware what they use is a VDS, or they use a GS that are interpreted by the window host script mother, and there are some debuggers included for us to load this text file. Those are text files, and we have some points to add to be executed, and in other cases we have another program that was created by one of my co-workers to load the file there, and you have you play, and whatever you want to add, it's quite easy to use, it's user-friendly, and that was done by one of my co-workers. Obviously, we need to know what happens with the operating system when we execute a sample. So for them, we have here from Microsoft, it's very useful, the internal things, and this program also with a capture of all the keys, all the registries from the system, and you can do whatever you want to do. You execute to the sample, and then you compare to see the keys modified, what's been deleted, and so on and so forth. And also there are tools like the one you see here to analyze documents in the case of Microsoft Office. It is what we can give to the machine in order to start, what we can upload. And let's talk here to start with Athena, Athenea platform. Athena. Who knows Athenea, Athena? who's played with all the challenges. You've taken the challenges. The two first challenges. Athenea, is a safety information technology, safety security platform where we have several challenges like cryptography, scenography, exploiting, networking, reversing, and what we're going to talk here is reversing. In this Athena platform, they created the school Athena School, for those who are starting security and information technology. There are some courses with the theory and tutorial courses with the challenges, but the difference is that you get solutions here. You can compare if you are on the right track, if you are doing well or not. So where to start with reversing? In the school, Athena School, in reversing category, we have computer architecture, we have the Intel's syntaxes, we have to know all the architecture von Neumann characteristics we describe here, the binary format of Windows, we define the portable executable format from Microsoft, theory of a de-ensemble compiler, decompiler, and the MSDN and so on, and the challenges from Athena. I was told to analyze Athena challenges in front of you, and those are old Athena challenges. Out of those 4 reversing challenges, I'd like to revise with you. I'd like to elaborate on the simple ones for those who are starting, and just to get a flavor of that. And then we're going to talk about another Matryoshka. The Matryoshka, it is one of the most difficult challenges of the platform of reversing challenges. And we'll start with the first one, the crack me if you can. Crack me if you can, and this crack me, the challenge is to obtain the key that is, or the code that will appear when the binary is executed in the proper way. So there is a difficulty embedded there, 2 out of 5 stars, and we get the binary and the hashtag. And whenever we see a new binary, I like to explain how it's been done and what has been used to do it, because you can get an idea on where to go, which tool you should use, and about the next steps to take. And then here, in this case, for instance, we check the file we've got. It's an executable, 32 bits for Microsoft Windows, and there is a tool I have described which is Detected Easy, D-I-E, to see the compiler. In this case, it's a Visual C, C++. That's the edition 2015 version, release 14. And then it seems here the entropy of the binary, and you see that it is not too high, this entropy, so they haven't used sort of blurring method. So when you want to take the decompiling and deassembling of the program, you see the real code that was created by the programmer. And then we take this and crack me if you can, knowing that we are able to see it as such. We upload at this D-assembler. It is, first of all, I prefer the static analysis to see the program flow, as it is Visual C, C++, as it was described by our colleagues previously. When you conduct a program in Visual C++, the entry point is not the main that was created by the programmer. The compiler puts a lot of code at the beginning, but with the experience and a bit of idea, you can see this is Hydra software. Hydra software, that's an open software nowadays with Hydra, and in this case we upload the program and we see on the left-hand side the entry point of it. We'll look for this, and then what's good here is that in parallel it synchronizes the decompiling with the deassembling. Once we have the entry point there, we see decompiling on the right-hand side, and there is a function to which we give 2 parameters, And in this case, we have 2 pointers, but in general, the truth is that this is a main, because you have here the arguments and you have here the value. Another way to get to the main would be to look for strains of characters in this, strings of characters, and to look for something striking. In this binary, we have CCN container, and then you would look for this string of characters, and here you could tell the system where was the string used, and then it will take you to the de-assembler where it was used, and you could go up levels to get to what you think is the main. It should be a function that will be Visual C++, that is where you have here array of characters and one figure. So we see here the representation of the pseudocode code created by Hydra on the main of the program, and what you see here is that there is an if condition that's huge. If it does not comply with this, that goes to 0, and it's finished. That's it. What in this if? There was an if, a condition sine qua non for the program to go on, to go ahead, and then let's see what happens there. And I would like to say that what we see here is parameter 1. And it should be more than 2, bigger than 2. In the main function, parameter corresponds to the number of parameters we have here given to this binary. It should be higher than 2, so we have 2 parameters to the program, and we'll see which 2 parameters are. There is another function that will give back another variable, a Boolean variable that is translated into a figure that, as you see here, it's different from 0. So we see that we have to convey 2 parameters, and let's see what the function does. The function, if we see here, the decompiler and the de-assembler of such method, we see it uses the create to help 32 snapshot. That, as I said before, if you go to MS-DN, which is the reference of all the ones of the operative system, is used to capture the process that are executing on the machine at the moment when you call the function, and then with 32 first and next, you go along the snapshot and you do whatever you want with it. If you look in detail the code of what's been done, there is a variable to which has been compared, which is an array with a string of characters. I don't know if you see it in gray. It's renamed here, and then the string chains are TCP/View White Shark, the protocol analysis software that is going to be used by the analyst, the software analyst, and it checks if someone is trying to spy, to see the program, and then to overcome this, you could have a breakpoint here, and you could make the opposite. In the case, you would have one of those, but let's see how to overcome this. You will have to take a look and not to have one of those softwares open whenever you are debugging or you are cleaning the program, the software. Once the function is, we pass this function, there is another function down here, part of the program, where there is a parameter, I don't know if you can see it here. The parameter is the first string that goes as parameter into the program, knowing that this is the first parameter given to the program. And what you see here is you have a call of the API of getComputerName, the instruction. And you have to be too clever to know that we're seeing the computer name, but you can go to MS-DN to see what the parameter is, the one that's got, and then you compare what is given back. to the parameter. The first parameter you have to convey is the name of our computer name. And in the case they do not get what is to be expected, then it is going to create another flow and this flow calls a function that is showing directly the window like as such. And this crack me if you can. If the name is the one that's unexpected, someone could think that's the key or the code or something, but there are other conditions and other tests to pass. Out of curiosity, if you look for the string of characters in Google with search for this, this is part of the Neil Stephenson's book, and perhaps you get an idea on this challenge and to what is related. And then we have here the program needs two parameters, and the first one is a computer name, and then we'll see number two parameter and what's going to be happening with this. There is another function here in the program, part of the program, comparing as it was the case. The first parameter was given to the first one, now the second parameter is given to the second function, and there are some operations going back to the right, going to the left, and so on and so forth. And this is in a case of a hard-coded string of characters. And then once they conduct those operations, they perform the operations, and if they compare this with a parameter and they coincide, this is going to be used as a code for deciphering code. It is in order to, we have here, for instance, hash data, we have a decode or whatever. It's decoding, clearly. It's decoding, deciphering. In the decompiling, this is not seen clearly, but we see the version of the deassemble, and we see that what is given back by the function goes as the local variable here as an input, and that is a local variable, and you see that it goes to the one receiving the code, crypt create hash, and the code is what stems from this function, what goes out of this function. And then once we have the code, we can have a program in C language implementing the same thing and to execute the program, or knowing that we have an idea and where it goes, we have a debugger, the X32DBG, and with the debugger now we could have breakpoints, that are those points to check that the analysis, the static analysis, does correspond with what we believe it is. And then in this item, in this point where we have the deciphering of this, we have another breakpoint comparing this with the parameter that was conveyed, and then we send another randomized parameter first. We see the characters, and then we know here we get the second parameter out of this. I have a video where I have done this, and I'm going to show the video to you. Video on, we have the entry point, then I have another one in this the main one. Look at this, I have another one here. Then we skip again, and we go towards the part where it's comparing with a get computer name. We see what's back from this. It's a name of my computer, and it's compared with Comando Uno, which was the name I gave at the beginning. So we go there, we check it, because we know the first one, we change the name, we swap, and we put the first name, we accept, and I don't know if the video is a bit blurry or not, but then we video again, we see it again, we execute again, we see that now it passes the test, and here it's comparing with a string of characters, and I think the video is not on time. We see what's been generated, the comparison. I have accelerated to see the process. Let's speed up, and then I have here note block where I have included all characters, and in the end it is Neil Stephenson was the string that appeared there. And then we swap it, we'll launch again the program, and now we see that we have the follow breakpoint. We see the comparisons will coincide now, and it is the side we wanted. They are comparing now the string of characters, and in the end, yes, that's end is okay. The end is that we get the flag of this challenge. I have this. If you want to do it, it's up to you. If you have the time, you know what to do, and please go ahead. And I wanted to trigger curiosity. You have to create the virtual machine and to play a little bit with the virtual machine. And now another item, and this is what I wanted to say, but I think that you're following me, yes. If not, during the Q&A session we can go back and see things. And now we're going to talk about the Russian puppets, the Matryoshka. And we're going to find out about the flag and to overcome this challenge that is especially difficult. This is Matryoshka. And then on top of this, and this challenge, we have a clue that we'll see if we're going to use this or not. It is think about the true ciphering, and that the zip code is infected. There is something added. It is a 5-star difficulty. It's we'll see if it is that difficult. And let's continue now. We get a zip where we have a binary code inside. We have the hashtag here, and we just extract the zip, and we see the binary out of that. And now the first thing striking me is that the header is a bit odd, it's strange. It's not the typical one, it's not P, whatever you see, the one where you have a sort, and no. It is sort of making us think that the compiler is not the standard one, not a well-known one, not the one I've seen till now, one of those I've seen till now, or they have used a type of packer. Let's see.
So we move to detected AC, and we see the entropy of the binary system is at a very high level, 7.999, so it's almost at 99%. This binary that we've been given is packaged. So the packers, the commercial packers, well, most of them have been analyzed by the community, and they created some signatures. Equally, there are programs where you have a binary system that could be packaged, and on the basis of these signatures, or on the basis of the execution, they tell you whether the commercial package, the packer, they tell you the commercial packer that they've used. With this detector, maybe the packer that they've used is MacCode compressor. So we know that it's packaged, and in order to see the app code as a programmer has done, we'll have to apply some transformations. We'll have to stop executing the binary. We'll see how to do it in order to see the app code. Anyway, just for the sake of curiosity, we're going to launch it to see what it is, and the app was this. It was a padlock that will ask us to type some kind of combination, and depending on what we type in, we will keep on moving. So we know what MacCode compressor is. And as the community has worked on this, if the first search that you do in Google is MacCode compressor in pack, you'll see 5 or 6, a great bunch of videos of people depackaging binaries that have been packaged with this packer. And the way of unpackaging them is, well, you watch the video and you say, well, this is exactly what, so let's see how we can do it. So in this case, it's quite similar to UPX. and we get to the entry point. We would continue through ESP in the uploading, and the address that we have, well, we would include a hardware breakpoint. We would let the binary execute, and we would come to the jump before the original entry point, just before the original entry point. And this is the entry point of the original program before being replaced by the packer. Okay, so we would tamper the binary, we would look for the import table of this new binary, and we would fix it so that the binary can be executed from the disk. And here we would check that the binary has grown from 1.6 megabytes to almost 5.8 megabytes, and it's still executable. So this way we have been able to retrieve the most similar things to the original code of the app, and we have something to see with our static analysis. So if we have a look at this this binary with detect-etc, we see that it has been done with Delphi, and we see that the entropy has been reduced to 5.35. So we're almost 100% sure that we'll be able to include some codes, and we'll be able to play around with it. So looking for characters as strains, we've seen that we have a pad, we have buttons, so button to one click, button to click. These strains were quite curious to me, and I saw that they were defined in a structure where above every strain there was an offset to a function. So I saw how the graphic interfaces in Delphi work, and these offsets are the functions that are dealing with the pulses of every button. So here they appear as button 1, button 2, and we have numbers, but we have to see that button 1 doesn't match number 1. So in order to see what every function does, we need to see the link between button 1, what button it really is in the interface. So for this, what I did was to upload the application in the debugger, and as we have the offsets here, I included a breakpoint at every offset so that it stops here to launch the app. For example, I click on A and I see what offset I've stopped. So if this offset is the one that I have here, okay, so button 1 is A. Repeating this with every button, we see that 1 is A, 2 is E, etc., etc. So in this array, we can see the strain and a function that is called funCreate. This function initializes the logic of the graphic interface to initialize variables, all the logic that the programmer has created for this interface. So if we have a look at this function, we see some variables that have been renamed, but initially you see that these are variables, as you can see on the screen. And if you follow the program areas where these variables are used, you see that there's an increase of this variable, and this is included in a button code. Specifically, this is included in button A. So these are counters of how many times you've clicked on these buttons. So there's a counter for button A, another one for button E, another one for button 3, and another one for button C. Okay? And what we can see afterwards is that this is moved to a local variable, and after that to a specific offset. That, well, these ones that you can see here. I noted them down because they are retrieved. This is retrieved from these offsets to compare it in other functions. So just to know, or to note down that button A is 980, the other one is 984, etc. And this is on one hand, and if you keep on seeing character strains on this binary, you see that on the one hand these strings are, some of these strings are quite big, and one of them starts with 4D5A header. This is the equivalent in ASCII2MZ, that is the header of a Windows binary. So we could suspect that in some way we would see where this has been used. We see that there's a function where it seems that there's another variable, and after that this variable moves to a function where there's a writing. Okay, so everything seems to indicate that there's another binary around that will be written in the disk when something happens. On the disk, sorry. If we keep on looking, we see the variable that has been copied, that has been renamed as EZ part 1 or chunk 1. We see where it is used, and we see that we are moving to other functions, and if you check that these are variables of the same type, they are following this order. So I guessed, and I saw that that was the case, that this was the order that the binary building was going to follow. So chunk 1, chunk 2, chunk 3, and after that I renamed all these functions, and I renamed the function as part 1 with variable 2 as part 2, and I looked at where these functions were called, and if you follow them, we can see that both part 1 and 2 are, well, the functions come in a row, and they are called in the offset code that manage the logic of button A. If you do the same for the other parts, which, well, you see that beforehand there are some requirements that we'll see, but if we do the same with the other parts, we'll see that for parts 3 and 4 and 5 and 6 are on the button OK, and 7 and 8 are on the button C. So it seems that these are the buttons that will participate in our pad, and the ones that we'll have to do something with. If we have a closer look to the the button A code, sorry, we see that it recovers the variables that we considered as counters before, and they're included in another local variable. And after that, there will be a comparison of that with other values that have been defined, that are fixed in the code. In this case, these are 4 and 0. So we see that it is recovering it, and when we click on it, was the function that executes when we push a button. So it checks how many times this button has been clicked, and it compares it with 4. With button E, and it's compared with 0, and button C with 0. So if we click on A for 4 times, at the 4th time this condition will emerge, and we'll see that there will be a file on the disk with t.tmp that contains the 2 first parts of what is considered as an EMZ. If we click on OK, it has dasif 1, and after that the other one. On the first one, well, these counters are global, okay, they do not change. So it looks how many times button A has been clicked. We don't have to click on A more times before clicking on OK. How many times we've clicked on E, 0, and 1 for C. So clicking on A for 4 times and clicking on C for 1, just once, we would have the parts 3 and 4. Do you get more or less get it? Well, exactly the same happens for the second part. A has to be 5 times, C one time, and we have the next parts. And with the button C, we have the same checks with the same with the other values, and in the end, it has a code that it just renames t.tmp to a.exe, and it launches the binary. Okay. So we could launch this on the debugger, and as far as we know the combination, we can include breakpoints in those offsets that we had to check that this is really the case. And we could include one last breakpoint before the binary executes. So as it's written on the disk, we would have it as such, and we'll have to see what we keep on doing with this new binary. So we would do this, and once we recover this new binary, that is a.exe, we repeat the process. the same again. We have a look at it to see what compiler we've used to create it. In this case, I've used this XAA info that tells us that maybe it is a Visual C++. We look at the entropy, and it doesn't seem that it's packaged. So we upload it again, and we perform another static analysis of this new binary. As it is with Visual C++, sorry, we would move to the entry point. We will, through a strain or having a look at the decompiler code, we would find the main function, or through an API that could call your attention, you would move to the part where the main code is. And the first instruction that we see is a get console window. We see the windows where it is, executing at, and if we have a look at MSDN, it says that it should be hidden. I don't know the prefix, but the program, as soon as it executes, will hide the window where it is executing this CMD or whatever. So after this, we see a stream of operations that you can include. You see loops, you can do things, and eventually you see that with all this, it doesn't do anything. It's stored in variables, it releases them, it reassigns them. Well, if you compare with the pi calculation algorithm, it was this. I mean, it's code to delay the execution. So you have to stop here, of course. You have to lose some time, or if you are very good and you see it, you say, oh, okay, that's fine. But after doing this, the next step would be something a little bit more relevant, and it's a function that is called with a new thread with create fur, and this function makes a hook to the DBG remote breaking API. This API is called when you have a binary that is executing and you tell a debugger to attach to this process, to debug it. So what it is doing here is to have a look where the API address is, and it is telling it to write down where that API is, to jump to where exit process is, so that when you attach to the binary, it calls exit process and it's done. It is an anti-attach measure. And here we can see before and after this API. If you keep on what the API is, you see that normally speaking it's push 8 and some references, and once this code section has been executed, you see that it jumps to exit process. Okay? So to skip this in debugger, you would have to note this call, or to note the write process memory call, for example, in order to avoid this hook from happening. We continue. There's more code than that makes different verifications, and what it checks are the permissions that this binary has to be executed, and it does it with these APIs, with the DEX token information with token elevation as a parameter, so we can see whether the program is being executed with the permission token, and it's telling us that the binary will have to be executed with administrator permission. On the other hand, it's true that we could skip this, but maybe this check is being done because maybe the administrators need some time of permission, so it's for free, so we can execute it as an administrator, and that's fine. On the other hand, as the previous Crackney did, it uses the create tool health to the two snapshots API to make a snapshot of the processes, and it goes through them and it checks, in this case, that our process's father, so to speak, should be a process with the name cmd.exe. It doesn't mean that it has to be cmd.exe from Windows. We could rename our debugger as cmd.exe, and this condition would be fulfilled, or including a breakpoint and skipping it. After that, more checks. We see, or it verifies that the Windows version that we are using to execute this, well, it's a little bit tricky here because it's a lif, and sometimes it jumps where we do not want it to jump, so it has to see that the Windows version is a Windows 7 on. And after that, it has a new thread. It creates a new thread with other function that we'll have a look at right now. And out of this thread, a variable is assigned or allocated, and we verify the not of this variable, so that we need to verify that this variable is set, so that it doesn't get into the lif, because we don't want that, because this moves directly to a code section that would delete the executable. So what do we have in this new thread? In this new thread, we have a call to get assigned key state, and if we have a look at MSDN, this is to log the keyboard pulses. And what does it do with this? It has a counter at the end. It checks that it's different from 12, and it increases every time we click on a key. So when we click on one key 12 times, it will get out of this code. We do not know what key it is, but we will have to see what it does with it. If this function, the 1417F0, that has the reference of what the user has just introduced, says that everything's correct, we would write the next 6 characters in a registry key that would be current user software interact, and it sets the variable that we were saying that we want to set in 1 to make the comparison later on. So what does this function do to compare the value? So as has happened before, we have a jet of code, a code jet. These are bit operations with a variable defined on other side. Equally, we can either try to copy this and make or create a program in C or in Python or wherever you want it. But in Python you have to be careful because this is roll and roll 1. It's taking the lowest part of the registry, so you need to use these variables or to use more faces or masks, sorry, to do it. If you don't have time, you can do it on C, or if you even have less time, executable. You have to launch the executable, and you have to include a breakpoint when the comparison is done between what you've taken out from here and what we've just included. So apart from all of this, you have to verify that the variable that we've passed is 12. We know that it has a length of 12, and you should check the 6 first characters of it, so that executing this function and doing these breakpoints, we'd be able to know are the 6 first characters that the binary is expecting. So this is what I've done here. I've stopped just before calling this function, and now I'm going to get in and I'm going to have a look at the comparison.
Entramos.
So we get in, we see the operations stream, the operations flow. We put a breakpoint right here. We execute it. And I'm still uploading memory of this variable that will be writing down. Initially, it's this. So now I'm going to perform the transformation. You can see how it's going to be executed. We execute it. It's a little bit stuck, but, well, you can see. And it is Atari, and if you have a look at Lexa, this is the space. Okay, so 6 first characters are Atari space. After this, there are more checks. it checks whether you are doing it in a virtual machine. In this case, the verification is through registry codes. When you install the less additions in a machine to make it compatible with the screen size, to make file copies, this leaves a trace in Windows logs that are these specific codes. So if we make a check and these keys exist, these codes exist, we know that we are executing it on a virtual machine. After this, there's another anti-debug measure. Well, we have the reference here. We can see how we use it, and it's calling an ENTDL API. This is another debug measure that we could skip changing registry, and that's it. So after all this, we would have the file writing with P name that you can see. You can see there. You have the buffer of what we're going to write. So we write this, that it seems at 64 strain, looks like a 64 strain, and it's going to write a P file with this content. On the other hand, well, I saw this before, but it made more sense to include this in this part because it is when it is used. It has a resource with the name 666, and after the ODP, it reads the resource and it takes it to another file with the name 1.ps1. So if we do not make some of these verifications a binary, we'll make a ping, and with this land would call bell and moves this and passes this strain, that is the name of its executable, so it's deleted. So it's another measure that makes analysis more difficult because we need to have a copy and we need to do this. So, okay, what have we got? What do we have? We have P and P.ps1. So we would execute it. We would see the different conditions. We write down Atari. They say that we are going to make